Okay, so here we're going to be taking a look at something called, well, there's Rolle's theorem and then there's the mean value theorem, and they are very similar to each other, and we'll talk about them and do a couple examples. So for Rolle's theorem, in this box I want you to write the definition, but over here we have the definition. It's basically if you have a continuous function, very important, in a closed interval from a to b, or the interval, open interval, so your endpoints can be included or not included as long as it's a continuous function. If you know that f of a is equal to f of b, now those are y values. Okay, so if you're looking at a graph, so let me just sketch a graph real quick. If you are looking at a graph, so here's a and here's b, and so let's say this is f of a. It is also equal to f of b. They're the same. But let's say your graph goes up something like this. It can be anything, okay? Then there's at least one number in C where the derivative is 0, meaning there's at least one point where there's a horizontal tangent. And the graph that I drew, it's going to be about right here, okay? Because the tangent line is 0, the secant line is also 0. So here's your secant line, and here's your tangent line. Right? So if f of a is equal to f of b, the secant line slope is 0, then there also has to be a tangent line whose slope is 0. Remember, tangent line goes through one point on the graph. A secant line goes through 2 or more. Okay, so let's make sure you get that written in there. Draw the little example. Hopefully that'll help. Let's do an example here. It says find the two x-intercepts of that function and show that the derivative is equal to 0 at some point. So go ahead and find the x-intercepts, find the derivative, and show that there is a derivative between those. Don't graph it, okay? Don't graph it. Try this on your own. And then pause the video and come back and see how you did. Back to see how you did. When you set the original function equal to 0, you should get the zeros of 1, x equals 1 and 2. So over here on our graph, the zeros are going to be at 1 and 2. Didn't really leave much room on this graph, I apologize, but those are where the zeros are going to be. Now, we know that it is concave up because this is positive. Remember, it's going to look like that, okay? And then our horizontal tangent occurs then when we set the first derivative equal to 0, it occurs at 1.5. So at x equals 1.5, our horizontal tangent is going to occur, so right in there. When we kind of sketch the graph, it's going to look something like this, quadratic. Then at 1.5, we have our horizontal tangent. And remember, do that in red here. And remember, the horizontal tangent here that we found, that's equal to the secant line right there. Okay, so that's using Rolle's theorem, showing that there's a horizontal tangent if there's a horizontal secant. So go ahead and try this example. The graph is a little better here, but let's say your function is x to the fourth minus 2x squared. Find all values of c in the interval where there is a horizontal tangent, and there will be more than one. So go ahead and find your zeros, then find where your first derivative is equal to 0, and identify all of those values where that first derivative is 0. Pause the video, try this, and then come back. When we go ahead and set them both equal to 0, for the original function, setting that equal to 0, we get x equals 3 values. So 0, -2, or negative square root of 2, and positive square root of 2. So I'm going to go ahead and put those on my x-axis. I know the graph crosses there. And then I also have my first derivative equal to 0 at 0, -1, and 1. So I'm going to put little hash marks there. We'll do purple. So at 0, -1, and 1. Okay. So when we sketch this graph, I know that it's going to come down here. It's going to have a horizontal tangent there, right? And then it's going to have another horizontal tangent at that point right there. And then have a horizontal tangent here, and then come back up. So the graph should look something like this, where my horizontal tangents occur here, here, and here. Okay, so that's the basic idea behind Rolle's theorem. Now let's take a look at the mean value theorem. The mean value theorem is similar. The only difference is if I draw a picture to illustrate it first. So the only difference here is that f of a, so let's say that this is a and this is b, f of a does not have to equal f of b. Okay, that's the only difference. Rolle's theorem, they did. So let's say f of b is here, f of a, so this is f of a, and this is f of b. Okay, you notice they're not equal, but in Rolle's theorem, they were equal. So that means when I sketch this graph, so it could look like whatever you want it to look like up there. It doesn't matter. But when I sketch this graph, I'm going to make it look like that, maybe. It's a weird looking graph. But I sketch it. What mean value theorem says is something very similar, that there has to be a point C between A and B that has the same slope as this secant line. So here's this secant line right there. And there has to be a point somewhere in here, maybe about right there, that if I drew a tangent line, the slope would be the same as the secant line. So we're going to identify this as your point C. Okay? So that's what the mean value theorem is saying. So it's very similar to the Rolle's theorem, except now f of a does not have to equal f of b, and your slopes do not have to be 0. So go ahead and copy down this definition. Again, it has to be continuous. That's extremely important. And this should look very familiar because this is the equation, old school equation, going back to pre-algebra and algebra 1, right, where you would have y sub 1 minus y sub 2 all over x sub 1 minus x sub 2. It's the same idea. This slope, but now this is the slope of the tangent line using calculus, and this is the slope of the secant line using algebra. That's the only difference, right? You're combining the two in this case. So copy that down, write down whatever you need to write down so that you understand it. Back to the video when you're done. Let's do an example here. So we have our function 5 minus 4 over x, find all values of c in the open interval. Now you don't necessarily have to graph it. You can if you want to, but all we're doing is finding the values of c in that open interval, so from 1 to 4, from there to there, that have the slope of the tangent line is equal to the slope of the secant line. Let's figure out what is the slope of the secant line. So right here. Okay, so go ahead and find the slope of that secant line, pause the video, find it, and then come back, and we'll continue from there. You have to evaluate when x is 4 and 1. So when x is 4, you get 5 minus 4 over 4 using this equation here. And that gives us 4. And then when f is 1, when x is 1, your y value is 1. So if we sketch those points over here, right? So you would have 4, 4, and 1, 1. So those would be the 2 points. And we're looking at the slope of that secant line right there. And you can look at the graph and see that the slope is, in fact, equal to 1. Now from there, we have to figure out where that value c in there. So go ahead and find the derivative, and we're going to find where that derivative is equal to 1. So find the derivative, set it equal to 1. Pause the video, try that, and come back. Now that you've tried it on your own, we went ahead and we are finding the derivative, which you can do low D high minus high D low. This 5 is a constant, so it drops out. Don't forget this negative, right? It's minus that. So low D high minus high D low all over low low gives you negative 4 over x squared when it's all simplified, but those two negatives make it positive. So then we set this equal to 1, and you could cross multiply here. I put that over 1. And you would get x squared is equal to 4, or x is equal to positive negative 2. Now in this case, look at our interval. 2 fits into this interval, but negative 2 does not. So we're only looking at x equals 2. So when x equals 2, it's going to be right there. Is the answer. The only place where the derivative is equal, the tangent line, the slope of the tangent line is equal to the slope of the secant line is at x equals 2. And if you wanted to sketch the graph, you could find f of 2. That's 5 minus 4 over 2, which is 5 minus 2, which is 3, right? So this occurs at 2, 3, where that's going to be equal. So it might look something, your graph might look something like that. Okay? Let's try one more word problem using the idea of the mean value theorem. The mean value theorem can also be looked at like this. So go ahead and read the problem yourself and then understand it, and we'll go from there. So read the problem yourself, understand it, and see if you can't use the idea of the mean value theorem, secant tangent line, to figure out how you could prove it. Looking to receive some help, just think of average speed, right? If you know that this truck traveled 5 miles and however long it took them, what did they say, 4 minutes, figure out what the average speed is, because then we can use the mean value theorem, which states, hey, listen, if your average speed, let's say you go on a run and your average, you know that you ran 10 miles in this amount of time, you can figure out your average speed. It's just distance over time, right? If you figure out your average speed is 7.5 miles an hour, then you know that at some point you had to be running 7.5 miles per hour in order for that to be your average. That's what we're proving here. So find the average speed and use the mean value theorem and what you know about it to prove that that person had to be speeding. You run distance over time. That truck went 5 miles in 4 minutes. So distance is 5 miles, and then to change it per hour, miles per hour, it's 4 over 60 or 1 over 15, and then 5 over 1 over 15 is 75. So you know that the average speed is 75 miles per hour. So that, then you know at least they're probably going faster than 75 at some point, but at least you would be able to write them a ticket for 75 miles per hour. You can't go over that because you can't prove that they did, but you know for a fact that at some point they had to be going 75 miles per hour, so that cop could give them a ticket for that amount. Okay, now down here, the alternate form of the mean value theorem, this should look familiar, right? It's just taking this mean value theorem that we talked about up here and rewriting it. So it's the same thing. It's just rewriting it so that it looks like this. And this is the equation for the point slope form, right? So y equals y plus x minus, however your books did this. That's the equation for point slope form, which is just another way to write the slope. Okay, so the alternate form of the mean value theorem is the same thing. You're just rewriting the variables. And that's it for mean value theorem and Rolle's theorem. Good luck.